The last concept we are going to learn this week is that of a star-shaped polygon. Imagine you're in a guided tour and the guide is telling you about what you can see around. Prior to starting the explanations, the guide will likely bring you to a point from which many spots of interest can be seen, and ideally all of those, so that people would only need to turn their heads when she brings their attention to the next object of interest. Should you be inside an exhibition hall, the best location to get an idea about what you might want to see inside would be the point from which you may observe the entire hall, simply making a full turn around yourself. So the question is whether such an observation point exists. A two-dimensional plan of the hall would likely represent a simple polygon. This leads us to introducing a concept of a star-shaped polygon we are going to formalize. A polygon P is called star-shaped if there exists a point Z interior to P or on its boundary, such that for any point T of P, the segment with the endpoints at Z and T entirely lies inside the polygon. If this is the case, we also say that the points Z and T can see each other. The set of all such points Z is called the kernel of the polygon. A polygon P is star-shaped if and only if its kernel is non-empty. An example of a star-shaped polygon is provided on the left in this slide. And this polygon is not star-shaped. To see why, consider its red and blue vertex. The region of P consisting of the points that can see the red vertex is highlighted light red. And the region of P consisting of the points that can see the blue vertex is highlighted light blue. Since those two regions do not intersect, no point of P can see simultaneously the red and blue vertex. And this implies that the kernel of P is empty. Note that the convex polygon is star-shaped and identical to its kernel. For a simple polygon with n vertices, its kernel may be computed in linear time. This is a result by D.T. Lee and Franco Preparati, published in 1979. However, the respective algorithm is quite complicated. A simpler way to obtain the kernel of a polygon consists in taking for each its edge E the half-plane bounded by the line through E that locally contains the interior of P in its vicinity, and then computing the intersection of the obtained n half-planes. This task can be accomplished in n logarithm n time. As soon as for a star-shaped polygon P we know a point Z from its kernel, the algorithm we have developed for testing point inclusion in a convex polygon can be readily applied to this case. The last observation we will make today is deriving the hierarchy of the classes of polygons we have considered so far. To make this more precise, convex polygons represent a subclass of star-shaped polygons, which in their turn constitute a subclass of simple polygons. This concludes the first week of our course. Thank you very much for attending.